Let's launch into chapter 2.5, the chain rule. When you think about the chain rule, I don't want you to think about a chain you might buy at the hardware store or the chain that you might use to put an anchor on a ship. I want you to think more about a chain you make yourself. Like remember making paper chains like this? Maybe when you were a kid, you'd put a loop on and then staple it together or tape it together and then another loop. So that's the feeling that the chain rule has here in calculus. You keep adding on a link, and you just miss out on that if you just buy the whole chain pre-made. So let's think back to derivative of sine of x, that's cosine of x. Let me be silly here and say sine of 1x. What would you say that's the derivative of that is? You'd probably say, it's cosine of 1x, right? Now, not every sine wave in the world has the same frequency, so we might try sine of 3x. Have you ever taken that derivative before? Well, on the finite difference quotient homework, you did, and you saw it still had 3 times the frequency as the original, but it was also 3 times taller. So it was 3 cosine 3x on the forward-backward central difference quotient homework. So now let's look for more patterns that might be going on. Let's try a new function. Let's try sine of x squared. And first question should be, who cares about that? Well, this is called a chirp. And it's important in radar and sonar, maybe LiDAR. From what I understand, the difficulty is when you transmit something in radar or sonar, it overwhelms the ability of your receiver to hear that frequency. It's like the sound is going from the mouth straight into the ear. And you need to be listening on a different frequency than you're transmitting. So here, you're changing the frequency as time goes on. And so when the signal gets back to you, it's at a different frequency than what you're transmitting right now. So another way to think of how the frequency is changing here is to say this is sine of x times x. So the second x here is just kind of time moving forward, and the first term, the 3 or the x, is the frequency, and here we can see that the frequency itself is increasing as time goes on. So let's try to guess the derivative. That's always fun. Maybe have one guess, maybe another guess, maybe another guess. So take a sec, write down some guesses, and then go check them in Desmos, and I'll see you in Desmos. Actually, before we get to Desmos, I want to show you the Wikipedia webpage for chirp. It's pretty interesting. So here's a graph of a linear chirp where the frequency is changing linearly. Here's its spectrum. We'll talk about spectrum later in the class, I hope. I would love to click on this, but it's so loud it would disrupt the video, so we won't click on that, but you should go click on it and listen to the chirp yourself. Here's a chirp with an exponentially growing frequency, and again, it's interesting to listen to. And there's some other good stuff on this page. But let's go to Desmos. So another way of thinking of a chirp is if you put your hand down at one end of a piano and run it all the way up the keys, that's basically an exponential chirp. So here I've got our sine x squared, and let's see what the derivative looks like. So does that match any of your guesses? What can we notice about it? Well, it's got an increasing frequency, just like sine x squared does. It also has an increasing amplitude. So what does that tell us about stuff? Let's go look at our piece of paper again. So you might have guessed based on these formulas that if the 3 popped out here but also stayed here, then you might say it's maybe x times cosine xx or x squared. You might have said, well, if we're taking the derivative of sine of x squared, the derivative of sine is cosine, and the derivative of x squared is 2x. So that would have been a reasonable guess. And did either of those match what we saw in Desmos? Well, this one just has a constant frequency of 2, but we saw the derivative had an increasing frequency, so it can't be that one. This one does have an increasing frequency and a linearly increasing amplitude, so let's go see if that holds up. Okay, we're back in Desmos, and we could say we do see an increasing amplitude in the derivative. Is it linearly increasing? Well, yeah, that looks like a straight line around growing up and down. This is just some numerical trouble, don't worry about that. Shows that calculators aren't perfect. So were we right with our f prime guess of x equals x times cosine x squared? Let's color that black maybe. Well, it's not matching the red curve exactly, is it? But it looks like it's just failing to keep up. Maybe it's not tall enough. So we could just put a multiplier in there maybe. And then adjust the multiplier until we match the red curve. Oh, too far. Yeah, that looks pretty good. K equals 2. Well, that's certainly plausible. So we could take the f prime divided by f prime guess, and we see a constant line at 1, which means we got one exactly equal to the other. Or if we had set k equal to 1, we would see that the ratio between them is 2. So that's where our k equals 2 came from. All right, let's switch back to paper and pencil. All right, so our newest guess is 2x times cosine x squared. This was a nope. It was almost. All right, so can we figure out why we might have a 2x out here when we didn't have a 2 times 3 out here? So write down your guess. So we might say maybe the 2x is the derivative of the x squared. I mean, 2x is the derivative of the x squared. Maybe that's why we get a 2x out here. So can you think of something else we can test where maybe something like sine x squared, where we could tell if we're getting the derivative of the inside thing out front? So take a sec to think about it. I'll give you a suggestion later. Well, how about now? How about sine of x cubed? So let's go check that in Desmos. All right, so let's change this to sine of x cubed. Whoa, that's crazy. Turn all that off. Okay, so there's sine of x cubed in blue, and the red, this might be hard to see. That envelope there, is this red line growing linearly? It kind of looks curved, or at least that one looks curved. Whoa. Okay, we might have overwhelmed Desmos. But that's actually looking kind of like a parabola, which would say that the amplitude is growing as x squared. So that kind of confirms it, I think. Let's go back to paper and pencil. Okay, so this did, so the derivative was maybe something like x cubed, x squared cosine x cubed. It's hard to tell. So what we were thinking here, let's go back to sine squared. So sine x squared prime seems like it is x squared prime times cosine x squared, and that is indeed true. Or you could think of it the other way. You could think of it as cosine x squared times x squared prime. So let's state the chain rule. So we're taking a function of a function here, so I'll call it f of g of x, and we want the derivative of that whole thing, and the chain rule says it's g prime of x times f prime of g of x. And note, this inside part here is not just x, and it's not g prime, it's just g. Another way to think of it is just do this product the other way. Kind of like I said here, it's f prime times g of x times g prime of x. And someone taught me a funny name for this once. We call this part d outer, like the derivative of the outer function. F is the outer function. This is the derivative of f, evaluated at the inner function. And if that's d outer, this must be d inner, or dinner. Okay, so the key skill in the chain rule problems is spotting what the inner and outer functions are. All right, so let's think about sine x squared. What's the inner function and what's the outer function? Well, I'd say the inner function is the x squared, and we call the inner function g usually, so we'll say g of x equals x squared. What's the outer function? Well, it's tempting to say f of x, but it's not really f of x, it's f of y, whatever g gives you. So you could say it's f of stuff, just to use a highly technical term, and that's sine of stuff. And if you want to abbreviate stuff to just the letter u, that's actually a lot of time what mathematicians use. So it would be sine of u. So then the derivative would be d outer times d inner, and that would be d outer is the derivative of the outer function. What's the derivative of sine? It's cosine, but then you still put in that same stuff. You still put in the x squared. You don't take the derivative. And then what's the derivative of the inner function? Well, we could write the inner function is x squared, take the derivative. So this is cosine x squared times 2x, which is what we found in Desmos. All right, so that is our basic chain rule and a straightforward chain rule problem. Now we'll get more complicated in the next video.